Let's solve a cool astronomy problem. The star Beta Doradus is a Cepheid variable star with a pulsation period of 9.84 days. We make a simplifying assumption that the star is brightest when it is most contracted, radius being R1, and it is faintest when it is most expanded, radius being R2. For simplicity, assume that the star maintains its spherical shape and behaves as a perfect black body at every instant during the entire cycle. The bolometric magnitude of the star varies from 3.46 to 4.08. From Doppler measurements, we know that during pulsation, the stellar surface expands or contracts at an average radial speed of 12.8 km per second. Over the period of pulsation, the peak of thermal radiation intrinsic of the star varies from 531.0 nanometers to 649.1 nanometers. First, we have to find the ratio of radii of the star in its most contracted and most expanded states. So let's write it. R1 over R2, we have to find it. So, first things first, we have to find the flux ratio. So we can write it this way. E1 over E2 equals 10 to the power of negative 0.4 times M1 minus M2. For flux, you can use any letter you want. Some people use E, some people use I, some people use F. It is whatever you want. Here we have to use our calculators, and here we find that the ratio is 1.77. From Stefan's law, we know that L equals to 4 pi r squared sigma 2 t to the power of 4. This is Stefan's law. So from it, we can write the ratio of E1 and E2 this way. E1 over E2 equals R1 over R2 squared times T1 over T2 to the power of 4. From this, we can find the ratio of radii. R1 over R2 equals to T2 over T1 squared times square root of E1 over E2. From Wien's law, we know that T2 over T1 equals to lambda 1 over lambda 2. This is the Wien's law. Sorry, Wien's displacement law, to be more accurate. Now we have everything we need. From this, we can find R1 over 2. R1 over R2 equals lambda 1 over lambda 2 squared times E1 over E2. We already know this. So then it will be 531 over 649.1 squared times the square root of 1.77. And from here we find that R1 over R2 equals to 0.89. Nice. Okay. Now we have to find the radii of the star in meters in its most contracted and most expanded states, R1 and R2, respectively. Okay, let's do that. R1, R2. Okay. We can write it this way. R2 minus R1 equals V times P over 2. Okay, great. So then it will be 1 minus 89 times R2 equals V times P over 2. And why do I write it this way? Well, I know the ratio that we just found. Okay, great. And now we have everything that we need. And from this, let's rewrite it this way. 1 minus 0.89 times R2 equals 12.8 times 10 to the power of 3 times 86,400 times 9.84 over 2 meters. So then we can use our calculators. We divide both parts with this. Sorry, like this. And here we can find that R2 equals 4.95 times 10 to the power of 10 meters, and then R1 equals 4.41 times 10 to the power of 10 meters. Great. So here's our second question. Okay, so let's move to the third question. We have to calculate the flux of the star, F2 or E2, when it is in its most expanded state. Okay, let's do that. Well, the easiest way to do that would be to get the absolute value of flux through comparing this flux with the observed flux of the sun. Okay, let's do that. Number 3. So here we can write it this way. M2 minus M sun equals minus 2.5 log E2 over E of the sun. Well, this is a famous thing. This is a famous formula. Okay, so from this we can find that E2 equals E of the sun times 10 to the power of negative 0.4 times M2 minus M of the sun. Okay, great. Well, we do remember that E of the sun equals to L of the sun, of course, over 4 pi A Earth of the Earth squared. Great, and we know that A of the Earth equals to 1 astronomical unit. Awesome. So here we can find that. Okay, let's rewrite it this way. I want to write it like this here, and then we would use the numbers. So 4 pi A of the Earth squared times 10 to the power of negative 0.4 M2 minus M of the sun. Okay. So M2 equals to 4.08, and the observed flux of the sun at this point would be minus 26.72. Okay, let's write it this way then. It will be 3.826 times 10 to the power 26 times 4.7863 times 10 to the power of negative 13. And we would divide it with 4 pi times 1. Okay, let's assume that A of the Earth equals to 1.496 times 10 to the power of 11 meters. I wanted to write it with 1.5, but then I realized that we have to be a bit more accurate with numbers in the problem like this, so we don't use this. We'll use this. Okay, great. So 1.496 times 10 to the power of 11 it is. Okay, great. And here it would be W over m squared. Awesome. Here we use our calculators. Just a second. And we find that E2 equals 6.51 times 10 to the power of negative 10 W over m squared. And this is the answer. Awesome. Okay, and the fourth question, the fourth problem. Find the distance to the star in parsecs. Okay, let's do that. Well, we can write it this way. E equals L over 5PD squared. We all know that, right? So then D of the star equals L2 over 4 pi E2. Well, then we can write it this way. It would equal to sigma R2 squared T2 to the power of 4 over E2. We get 4 pi here and 4 pi here, but I prefer not to write it. Okay. So then we get something like this. R2 T2 squared, yes, times sigma over E2. Well, the square root of it. Okay, great. So from Wien's law, we can find that T2 equals 2.898 times 10 to the power of negative 3 over lambda 2. Okay. And okay, we have everything we need. Then D star, after we put all the numbers into this, we get that D of the star is 9.208 times 10 to the power of 18 meters, which is about 298 parsecs. Well, you can get some different numbers. Well, maybe about 300 parsecs. It all depends on what numbers you actually use. But overall, there's an answer. Thank you.